All right. Hi folks, welcome back to Math with Captain Rod. The purpose of this video is to demonstrate how to use trigonometric substitution on appropriate integrals. So what we're going to look at here is integral 1 to e of dx over x plus root 1 plus ln x, the quantity squared. All right, and the first thing that comes to mind, this thing's probably going to need to be simplified down some. So I'm going to go ahead and make a substitution here to simplify it, and I'm thinking I'm going to let u equal ln x, and what that'll do for me is it'll turn this bottom into a square root of 1 plus u squared, which is a lot nicer looking quantity than square root of 1 plus ln x squared. Now when you do a substitution, I always recommend change everything here. So if u is ln x, then du is going to be 1 over x dx. Talk about the limits now. If x is equal to 1, then u is going to equal the natural log of 1, which is 0. And then if x is equal to e, then u is going to equal the natural log of e, which is 1. So our new integral now is going to be integral 0 to 1. Now I'm going to take a look here. Dx over x is equal to du, so there's a dx over x. That's going to be a du, and then the bottom is going to be square root 1 plus u squared. So the first step in this problem is a transform here, an algebraic type of transform here to take this from a logarithmic function, or from a logarithmic problem to a purely algebraic problem. All right, now let's take a look at this. Integral of du over square root 1 plus u squared. So this reminds me of Pythagorean theorem, and again, that's always my clue that trigonometric substitution probably will be important or probably be helpful. I'm going to go ahead and just get rid of this now because I don't think I'm going to need it. And when dealing with trig subs, first thing I always do is I write out Pythagorean theorem in its trig form, which is going to be, I'll write it right here, sine squared theta plus cosine squared theta is equal to 1. And as I look at this, right, this is 1 plus something squared. If I put either of these terms on the right, it's going to be 1 minus either sine squared or cosine squared. So this is not the form that we want. You can get other forms of this theorem either by dividing by sine squared or by cosine squared. I'm going to go ahead and divide everything by cosine squared. This is going to become tangent squared theta plus 1 equals secant squared theta. And as I look at this form, I'm kind of liking what I see because I look over here and I see 1 plus something squared, and I look right here and I see 1 plus tangent squared. So a substitution that looks like it will help is going to be this. I'm going to come over here and write, let's let u equal tan theta. If we do that, du is going to equal secant squared theta d theta. Now let's talk limits. At our bottom limit, we're going to have 0, not theta. 0 is equal to tangent of theta 1, which is going to give us a theta 1 of 0. And then at our top limit, we're going to have 1 equals tangent of theta 2. So again, solving this one, theta is 0, and solving this one, theta 2 is pi over 4. Take a moment here and just pause this and take a little break. All right, so I'm back. The idea now, we're going to rewrite our integral. I'm going to write this as the integral from theta 1 to theta 2. So in this problem, that's going to be 0 to pi over 4. Du is equal to secant squared theta d theta over square root of 1 plus u squared, and again u is tan theta, so this is going to read 1 plus tangent squared theta. Now, as we take a look at this, 1 plus tangent squared theta, and I look up here, 1 plus tangent squared theta is equal to secant squared. And then this is square root of secant squared, which is secant. So what we're going to have now is the integral secant squared theta d theta over secant theta. Again, 0 to pi over 4. And we can lose one of these secants, so now we got the integral 0 to pi over 4 of secant theta d theta. All right, so at this point now we've reduced this all the way down to a nice, relatively simple or relatively harmless form. Now there's a little trick to integrating secant theta, so what I'm going to do here is I'm going to pause this again, and I've got some helpers here, and I'm going to ask them if they have any questions. And I'm going to clean up my screen here a little bit, and then I'll come back and deal with this integral secant theta d theta. All right, how are we doing so far? First substitution good? Better be, I guess I erased it, huh? Second substitution, again, important things. Why a trig sub? Because that's a square root of 1 plus u squared, which just looks just like Pythagorean theorem. 2, which trig sub? You use Pythagorean theorem to tell which one. And I'll try to choose an example here next that it'll be a different one. All right. The rest of this is the algebra. You got to be a little bit up on your trigonometry to make these things work out right. So you have to know, your sines, cosines, tangents of appropriate angles. But, if u is tan theta, du is secant squared theta d theta. And then you just put in, 0 for u to get your theta 1, and then 1 for u to get your theta 2. Rewrite the integral. Boom. And this step is why we did that, going from here to here. Because you see how the integral just completely simplified down to just integral secant theta d theta. Now we got something relatively simple. Okay. Does everybody have this? Can I get rid of? I'm going to get rid of a bunch of this and just start working on this integral now. Give me a second here. Okay.